Welcome to my presentation of contributions to the efficient and parallel Jacobian evaluations and its application in OpenModelica. My name is Andreas Heuermann and I'm a research engineer at Linköping University in Sweden. I'm working on OpenModelica for a bit more than 2 years now and mainly focusing on the topics backend, C simulation runtime and FMI. You never used OpenModelica before? Try it out yourself. Or find us on GitHub and contribute to the project yourself. This work was created during the Paradigm project during my time at the University of Applied Science Bielefeld in Germany. I started working on the efficient evaluation of Jacobians in the middle of the project and worked mainly on the final implementation and wrap-up. Today I want to talk about the results related to efficient and parallel Jacobian evaluation. We will start with a short introduction where to find Jacobians in Modelica tools, and then I will present 2 approaches to speed up Jacobian evaluations. We will conclude with some benchmarks and a short outlook. We need numerical approximation and exact symbolic Jacobians in several different settings. The implicit integration methods, for example Dussel or Sandal's IDA, rely on numerical derivatives. For them speed is the focus. In Modelica, big algebraic loops with expensive right-hand sides are very common and need derivatives as well. Of course, optimization relies on first and second order derivatives, so there's room for a lot of improvements. Also, the next FMI standard will probably get a directional derivative function. And finally, we need derivatives in different places inside the OpenModelica compiler itself. To see how big the impact of a Jacobian evaluation is compared to the whole system, we did a little test with distribution system linear from ScalableTestSuite. And as you can see, the simulation time of the Jacobian TJac can make up a big portion of the total simulation time. So accelerating Jacobians could lead to a significant reduction in total simulation time. But how does OpenModelica compute Jacobians? To answer this question, we need a bit of notation. On the left hand, we have a Jacobian matrix defined, and on the right, we define a directional derivative df with seed vector dx. So, using the identity matrix I and the unit vectors, we can evaluate n-directional derivatives to construct Jacobian. Applying this on the DIE system f, which shall be equal to 0, we get our desired partial derivatives dz from an input seed vector dv. Here z are the unknown variables, meaning the state derivatives and the algebraic variables. V are known variables, and t is of course time. We need to transform this into an explicit system by applying BLT transformation. Please note that we define the system as h and that it is linear in the unknown variable dz, so we only need a linear solver to solve the system. And of course we can, and actually did, color this, so using coloring instead of the identity matrix works as well. To accelerate the Jacobian evaluation, our first approach is to reuse constant parts of the Jacobian instead of computing them over and over again. In the second approach, we utilize parallelization to evaluate multiple columns at once. First, let's look at an example. What sort of constant parts do we have inside a typical Modelica model like this reuse constant parts model? We have some simple sine and cosine functions and some expensive function foo in lines 6 and 7. We will compute helper variables called CSE for common subexpression to save the value for sine of x1, foo of x2 and cosine of y1. Now, when we compute the derivative, we get a bunch of equations. Don't worry, we are not going to read them all just now. The important part is that we get some new constant function evaluations independent from the seed vector dv. Those are the marked functions in blue. Here bar is the derivative for foo, and for those we will generate new CSE variables that are only needed inside the Jacobian evaluation and not during the normal simulation time. And this is how we would split the generated code as pseudo-C code. First we have constant equations independent of the seed vector, and then dynamic equations that are recomputed for each seed vector. That's the general idea if we have no loops present. Now let's have a look again at our system H we defined some slides before. We know that the calculation of H is independent from the seed vector dv. That's the way we defined it. So, if no algebraic loop is involved, we can use this calculation and only need to evaluate equation 1 once per Jacobian evaluation to compute our directional derivative dz for different seed vectors dv. The implementation is working on single expressions and using the wrap function call module to collect them. But until yet we have only looked at models without any loops, pretty boring. So we need a bit more notation to continue. When we apply matching and sorting on our DAE system F, we get the causalized system G. Here nx is the number of potential states and ny is the number of algebraic variables. Rewriting the causalized system G again gives k implicit systems of equations small gi. Those can be simple equations or whole algebraic loops, and each gi is utilizing previous computed values of z to compute new values for z. When we now look at an algebraic loop of gi and differentiate it equation-wise, we get the equation system you can see on the right side of the slide. Rearranging this into explicit form again, we get a linear system to compute the directional derivative of zi. Now, the most computationally expensive step to solve the system is computing the LU factorization, but luckily the factorization is constant for every Jacobian matrix construction, so we do it only once. In the benchmark section we will see that this reuse of constant parts has a huge impact on the total simulation time. Now let's have a look at the second approach to accelerate Jacobian evaluations with parallelization. Nowadays, the overall performance of a system is driven by increasing the core count, since further scaling of single core frequency has reached physical limits, meaning overheating or power consumption. So we tried to utilize parallelization using multithreading for the evaluation of independent Jacobian columns. On this frame you can see the simplified code for Jacobian construction in OpenModelica. To fit everything on one frame, we are ignoring coloring or documentation in this code snippet, but that works the same way. We can see that the Jacobian is constructed column-wise by evaluating the function directional derjac A for different seed vectors. You can see this in line 3. And as we have already seen, these directional derivatives are independent of each other. So we have a bunch of Jacobian columns, meaning the directional derivatives dx, and we try to distribute them to different threads on the processor. That is what this figure should show you. So each simple equation and equation system must be evaluated and solved for a different seed vector in parallel. To do this we used parallel for loops from OpenMP, but before we had to change the way Jacobian data is stored so that it's thread safe. The main challenge was to get linear solvers that are usually not used in parallel to work thread safe. The approach we have chosen is quite simple. Just give each thread its own copy of the Jacobian data structure, including potential linear systems. But even this straightforward approach took some time to implement in OpenModelica. And finally we added the same for colored and compressed Jacobians as well. A few words why we did choose OpenMP for this task. The OpenMP API is widely supported by all major compilers and most operating systems. The provided parallel for loops are very well suited for our codebase. And the fork-join model is well suited for our program. We have a sequential simulation, parallel Jacobian evaluation, and again sequential simulation. Now let's have a quick look at some results for our presented approaches. We used an Intel Haswell node on the high-performance compiling system Taurus at Technical University Dresden in Germany. To obtain reproducible benchmarks, we disabled hyperthreading in turbo mode and used the CPU's base frequency of 2.5 GHz. We will look at two models from the ScalableTestSuite, which can be scaled by parameters n or m. We start with the reuse of constant parts for colored symbolic Jacobians. Test model heating system L has a lot of Jacobian evaluations, approximately 55,000 for n equals 20 and 190,000 for n equals 80. Around 50% of evaluations are recognized as constant, which are mostly simple trigonometric functions, but a huge number of them. On the left part of the table you see evaluation time without the reuse of constant parts, and on the right side with the reuse of constant parts. The speed up we gained is around a factor of 1.8 to 2.0. For distribution system linear n, 64n, even more equations are recognized as constant regarding the seed vector. But because the Jacobian evaluation has a smaller portion of the total simulation time, we only get a speed up by a factor of around 1.7. And now let's look at the parallelization approach again for distributed system linear, but for different n and m. Since the columns of the Jacobian matrix are independent from each other, and our implementation is free of explicit synchronization constructs, we were expecting near linear scalability. And on the right side, you can see the dotted line as an ideal linear scaling, and that our results are not that far away from it. For all three model sizes, the speedup curve is close to being linear. Of course, we get some parallelization overhead from loop scheduling. For the maximum number of threads used, we suspect to have some slowing down because of synchronization on OS level. You can see this when looking at the blue dots and red crosses for 24 threads used. But for the biggest model with n equals 28, marked by the green triangles, the computation portion overlays this OS overhead, and there's no such a big drop in speedup. We also analyzed and measured the effects of different loop scheduling algorithms that OpenMP offers. They can have a serious impact on the scaling behavior, but we don't expect big load imbalances for those directional derivatives. After all, they are evaluating the same equations only for different seeds. Those algorithms are in short static. It divides the loop in approximately equal chunks which are assigned to available threads. Dynamic. The iterations are distributed to teams of threads. Each thread executes a chunk of iterations, then requests another chunk. The default chunk size here is 1. The guided algorithm is similar to the dynamic one, but the chunk size is proportional to the number of unassigned iterations divided by the number of threads in the team, decreasing to 1. And finally, we have the auto algorithm. The decision is delegated to the compiler and or the runtime system. We did run some benchmarks with different models for the different scheduling algorithms. Here you can see distributed system linear nm with n equals m for two different sizes of n. All in all, the differences are marginal. Only for the smaller model on the left side, you see a significant performance drop for auto and static. But for the bigger model on the right side, the drop gets smaller. We suspect that the computation portion for each thread was getting so small that the scheduling had a significant impact on overall simulation time. So we did stick with the auto algorithm so the user doesn't have to change anything for his system. Now we have a short conclusion and outlook. We could speed up many models from ScalableTestSuite, but for some, the implementation is not able to find all constant parts. Those are mainly inside arrow equations or function calls inside function calls, like in media. The parallelization also shows good results on smaller machines like my 4-core laptop, and the exact same approach can be implemented for the numerical Jacobian evaluations as well. Currently, there's also a symbolic Hessian matrix for optimization in the making, and this screams to be parallelized. Both techniques displayed satisfying results, so implementing them into the main development branch of OpenModelica is highly desired. Actually, the parallelization is inside the master branch already, but needs to be compiled manually at the moment. To get it enabled per default, we needed to add it to the build system so that everything works on all supported platforms. Thank you very much for your attention, and I'm looking forward to hear your questions in the Q&A session afterwards.